Here I want to address why the Earth isn't a snowball. So Earth is in space, and space is cold. And you would think, possibly, that Earth could just be a big chunk of ice, but it isn't. And understanding why the Earth isn't a snowball really gets at the heart of patterns of energy partitioning. So we know that a lot of the energy that comes into the Earth is absorbed. It's absorbed by the atmosphere, it's absorbed by clouds, it's absorbed by the terrestrial surface. But what happens to that energy after it's absorbed? To understand that, we really need to get at the partitioning of energy flux into three different components. So when shortwave radiation is absorbed by terrestrial surface, there's really three fates of that energy in the short term. The first one is what we call sensible heat flux, the second is latent heat flux, and the third is ground heat flux. There really are three fates of energy that's absorbed by the terrestrial surface. The first is sensible heat flux, the second is latent heat flux, and the third is ground heat flux. Sensible heat flux is the upward transfer of heat by the air immediately above the terrestrial surface. So the surface of an ecosystem heats up, and then long-wave radiation is emitted, but it's immediately absorbed by the air above it. And that causes that air to heat up. And that, as that air then subsequently rises, that is a flux of energy from the ecosystem from the atmosphere, from the air surrounding that terrestrial ecosystem. And we call that sensible heat flux. So it's sensible in the sense that you can feel it because that air is hot and it's generally rising upwards too. And that's a flux of heat from an ecosystem. We call that sensible heat flux. The next is latent heat flux, and that's really just essentially the evaporation of water. So it takes a lot of energy to evaporate water, and as water evaporates, it absorbs that energy, and generally it's transported from the ecosystem, again, through upward movement of air. And so that's a second flux of heat, latent heat flux. And then the third is just ground heat flux, which is really the short-term storage of heat in the ground. So if we think about partitioning, energy is going to come in as far as shortwave radiation, for example, is concerned, and it's going to heat up the surface of the Earth. Some of that goes into the ground, and that's called ground heat flux, and later that'll get generally re-radiated during colder times, for example, in the night or during a colder season. And then really in the short term, two things can happen. The air surrounding that surface can get heated up, and then because it's hot, it tends to rise, and that's sensible heat flux. Or it can evaporate water, and that evaporated water rises too, and that's our latent heat flux. So those are the two main ways that energy ends up leaving an ecosystem after it's been absorbed. Now, one of the things that's important to think about is that there's big differences if you take a look across ecosystems in how hot the surface gets. So generally we think of temperatures as far as air temperatures are concerned. That's what's reported in weather reports, and that's generally what we think of as how hot an area is based on its air temperature. And that's generally assessed at somewhere on the order of a meter and a half up above the surface. But the surfaces can get a lot hotter than the air temperatures, and actually the hottest recorded surface temperature was 70 degrees Celsius. And if you take a look, this is a map of maximum land surface temperatures that were remotely sensed. So you can see that there are some places where the temperatures don't get that hot, even in relatively equatorial areas, and other areas that get very, very hot. And understanding why some of those surfaces get hotter than others really has to do with sensible and latent heat flux. That's going to be something that's discussed more in Chapter 4. So then the question is, what happens to that heat? Well, a lot of the heat ends up getting re-radiated and eventually is absorbed again by a lot of these gases in the atmosphere. And we talked about this, how methane, different nitric oxides, oxygen and ozone, carbon dioxide, water, for example, all absorb long-wave radiation and then often re-radiate that and heat up the surrounding area too. Together, when we take a look at the atmosphere, you can see that there are small windows where long-wave radiation can escape. But also, depending on what the concentrations of these gases are, a lot of that energy gets reabsorbed and re-radiated to heat the surrounding area. In total, the global mean surface air temperature is about 14 degrees Celsius, if you were to average that out over a year over the entire Earth. And most of that air temperature is because of which gases we have and their concentrations in the atmosphere. And if those gases weren't there, if we didn't have water vapor, if we didn't have CO2, for example, the average temperature at the Earth's surface would be about 33 degrees Celsius colder than it is today. And that would be enough to take Earth and turn it into a big snowball. Now, another way to take Earth and turn it into a snowball, which has happened in the past, is really to get to the point where it gets covered a lot by this highly reflective snow. And once you get that, you get high albedo and a lot of reflection of energy, so that the air surrounding it really doesn't heat up. But if we didn't have all of those gases in the atmosphere, it would cause almost very little retention of that heat and a large amount of the water that we have to end up becoming ice and turning Earth into a big snowball. Now, it's important to realize that we have made the statement that for all intents and purposes there's energetic balance for the Earth, that the amount of shortwave radiation that comes in is balanced by the amount of shortwave radiation that's reflected away, as well as the amount of longwave radiation that is radiated out to space. But actually, a small imbalance in the energetic balance of the Earth currently exists. So when we do really careful measurements, we see that somewhere in the order of 0.26% of the incoming radiation is not released. It's being absorbed by the Earth. And that means there's a gain. There's energetic gain. Now, most of this energy right now is being absorbed by the ocean. And that's causing water to expand. So there's thermal expansion of the oceans. And that's been a big sink to the additional energy that the Earth has been gaining. It also causes the sea level to rise. So as that ocean water expands, the water itself expands, and that causes sea levels to go up. And also some of that extra energy that's being absorbed right now is going into the melting of ice. And so because of the buildup of greenhouse gases in the atmosphere, we're not quite in energetic balance, and a small proportion of that extra energy is being retained within the Earth, and a lot of that is going into the oceans and going into melting ice. Now, in summary, we're going to talk a lot more about sensible and latent heat flux in Chapter 4, but that's a really important component to think about, that when we're going to talk about the energetic balance of ecosystems, a lot of it has to do with how much of that energy gets absorbed, and if it does get absorbed, how much of that goes into heating the air surrounding the ecosystem, and how much of it goes into evaporating water. And that really controls the microclimate of areas and essentially the climate in the long term. And the last important point to re-emphasize is that the absorption of long-wave radiation heats the Earth, and the amount of absorption that we have is going to be dependent on what the albedo is of the system, but also how much of that energy goes in into different components of sensible versus latent heat flux, and then also how much greenhouse gases are in the atmosphere. So we talked about water and CO2, for example, and other components such as methane that absorb a lot of long-wave radiation. And these are really the factors that make Earth habitable today and are importantly determining what the temperature of the Earth is and will be in the near future.